In this video, we will investigate one more example of starting with a function and determining where it is concave up, concave down, increasing, decreasing. So for the function that we have x over x squared plus 1, the first step is to determine increasing, decreasing, which means we need the derivative of the function. In order to differentiate the function, we are going to have to use the quotient rule. So we take low d high, and the derivative of the function in the top is simply 1, minus high d low, and the derivative of the function in the bottom is 2x, and we divide by x squared plus 1 quantity squared. And if we simplify in the top, we have an x squared minus a 2x squared. So this becomes 1 minus x squared over x squared plus 1 quantity squared. And what I would like to determine is where is this first derivative equal to 0? Well, a fraction is equal to 0 when the top is 0, so x equals plus or minus 1. So on our number line, we indicate minus 1, positive 1, and we think about the sign of f prime in between. So if we go back and look at the simplified version of f prime, we see that the bottom is always positive because it's a square, so we really just have to think about what's happening in the top. You know, when is this 1 minus x squared? Positive or negative? And f prime is going to be negative to the left of minus 1, positive in between, and then negative after 1. So the function will be increasing on the interval minus 1 to 1, and decreasing on the interval minus infinity to minus 1, and 1 to infinity. So this is the first part. The next part is to determine where the function is concave up or concave down. So what we need to do is determine the second derivative. So the formula we have for the first derivative is 1 minus x squared over x squared plus 1 squared. So we need to differentiate this using the quotient rule. So we get low d high, so that would be x squared plus 1 quantity squared times the derivative of the function in the top, which is minus 2x, and then we subtract away from this. So it's low d high minus high d low, so we take the function in the top times the derivative of the function in the bottom. So by the chain rule, this is going to be 2 times the quantity x squared plus 1 raised to the first power, and then we multiply by the derivative of that inside function, 2x. And it is all divided by the bottom squared. So x squared plus 1 and a square squared is a fourth power. And what we're going to see here is a very typical algebra step, is we notice that we really have kind of 3 terms going on. One term in the top, a second term in the top, and the bottom term. And each of these terms contain the quantity x squared plus 1. So what we are going to go ahead and do is just cancel off one of those x squared plus 1s. So that new power in the top is going to be 1. The x squared plus 1 in the second term is going to go away, and the new power in the bottom will be 3. So in the top we will have minus 2x times x squared plus 1. And if we look at the terms remaining, we have minus 2x. So that's going to be minus 4x. So minus 4x times 1 minus x squared. And this is all divided by x squared plus 1 cubed. And the top, through just a smidge of algebra, simplifies nicely as 2x cubed minus 6x. And this is all divided by x squared plus 1 cubed. And what we would like to know is where is this equal to 0? And the only place this is equal to 0 is when the top is 0. So this reduces down to 2x cubed minus 6x equals 0. So 2x times x squared minus 3 is 0. So the second derivative will be equal to 0 when x is equal to 0 or x is equal to plus or minus the square root of 3. So on our number line, we need to indicate 3 points. Minus the square root of 3, 0, and positive the square root of 3. And what we need to see is where is the sign of f double prime positive, where is it negative? And looking at the form that we have for the derivative, x squared plus 1 is always positive. So the sign of f double prime is going to be specifically determined by the numerator. So we just need to pick test points and think about what's happening to this quantity 2x times x squared minus 3. So if I plug in a large negative number, 2x is negative, x squared minus 3 is positive. So f double prime is negative to the left of minus root 3. If I plug in the number minus 1, we would have positive, if I plug in the number minus 1, we'd have negative times a negative. So f double prime is positive. If we plug in the number 1, positive times a negative. So our function f double prime will be negative. If we plug in a large positive number like 100, positive, positive. So f double prime is positive. So our function will be concave upward on minus root 3 to 0 and root 3 to infinity, and it will be concave downward from minus infinity to minus root 3 and 0 to root 3. And one thing to note here is that there's quite a bit of work that goes into determining these intervals of increase, decrease, concave up, concave down. So as you're working through these problems, don't be afraid to take your time, use plenty of space. There's nothing wrong with using, a full sheet of paper or even more for a single problem. And make sure that you double check your work step by step as you go along. So let's put this information together and just provide a rough sketch. So I've gone ahead and labeled down below all of the information that we determined on the previous slide. And I've also noted that if we just inspect this function f of x, it crosses through the origin. F of 0 is 0. Additionally, the bottom is always positive, so if I plug in a negative input, our function itself will be negative to the left of 0, positive to the right of 0. So roughly speaking, I'm just going to go ahead and sketch something that could work here. So we start off to the left here, decreasing, concave down. So decreasing, concave down. Once we hit minus root 3, our concavity changes to concave up, but I'm still decreasing. But when I get to minus 1, we change to increasing. And I increase to 0, and note I'm still concave up, but at 0 I change from concave up to concave down, but I continue to increase. At 1, we switch to decreasing, but we remain concave upward until we hit root 3, and then we change to concave downward. So just a very rough sketch that satisfies the characteristics that we've labeled below. Decreasing concave down, decreasing concave up increasing, concave down increasing, concave down decreasing, concave up decreasing. And at first these problems seem a bit tedious, which they most certainly are, but sketching these graphs and coming up with intervals of concavity are things that the more we practice, the quicker, the more efficient they will become. Now another type of problem that we could encounter is to maybe take all of this calculus out from the beginning of the problem and just say, we're going to give you a function that satisfies, some given properties, and we just want you to sketch such a graph. So just more curve sketching practice. So I want f of 0 to equal 0. So f of 0 equals 0. I want f of 2 to be 4. And I would like f of 4 to be 6. Additionally, we note that f prime of 0 and f prime of 4 equals 0. So that's telling us at 0 and 4, the tangent line to our curve is going to be horizontal. So we'll keep that in mind, and we'll see how that works in a moment. For the first derivative is positive for 0 to 4. So 0 to 4 we are increasing. And it's negative to the left of 0, so decreasing, and to the right of 4. The second derivative is positive for x less than 2, which tells us our function will be concave upward. And it is negative when we are to the right of 2, which means that our function will be concave downward. So let's see if we can put this together. Starting off to the left, our function is decreasing and concave up until we hit 0. So decreasing, concave up. When we hit 0, we continue to be concave up, but we change to increasing until we hit that point 2. At 2, we continue increasing until we get over to 4, but our concavity now is concave down, and then concave down and decreasing. And notice when we put all this increasing, decreasing concavity into play, there was this requirement I didn't really write much down about, which was the derivative being 0 at 0 and 4. If you investigate the point at 0, notice that tangent line is horizontal. So f prime of 0 is 0. If you investigate the point at 4, the tangent line is horizontal once again. So f prime of 4 is equal to 0. And when we change our graph from decreasing to increasing, or increasing to decreasing, you have these natural points where that first derivative is going to be 0, where the tangent line is horizontal. Something we will investigate in future sections.